We're taking aim at one of the most frustrating, misunderstood, and honestly, flat-out expensive habits in our industry. I'm talking about firing the parts cannon at starter problems. Today, we're going hunting. We're tracking down an invisible enemy that's just quietly assassinating perfectly good starters and batteries right under our noses. And that enemy? Starter circuit voltage drop. Okay, let's dive right into this.
Here is our game plan for today. We'll start with the parts cannon problem, then move into the physics of starter failure, tackle modern tech and heavy diesels, run through the multimeter load test, learn about pinpointing the hidden faults, and wrap it all up with maintenance and repair standards.
All right, Section 1, the parts cannon problem. Why perfectly good parts die.
I gotta ask you rookies a serious question. Picture this. A customer rolls in with a slow crank. You swap the starter. Boom, out the door. A week later, they are back on the hook. Okay, so you swap the battery. 2 weeks later, same exact problem. Why do these perfectly good, brand new, expensive parts keep failing? Well, it's because you treated the symptom, not the disease. You totally miss the unseen resistance hiding in the electrical path.
A lot of you will just grab a voltmeter, touch the battery posts, see 12.6 volts, and declare the cable's perfectly healthy. You might even pat yourselves on the back for a quick diag. But here's the truth. Static voltage checks are completely useless for starters. Why? Because our invisible enemy, maybe it's corrosion hidden deep inside a cable jacket, or a nicely painted ground connection, it only reveals itself under the massive stress of a cranking load. When the system is just sitting there at rest, there's zero current flowing, which means zero voltage drop. It looks totally innocent, right up until you actually turn that key.
Moving on to Section 2, the physics of starter failure. Let's bring Ohm's law into the shop.
Let's unpack what the math is actually telling us here. Ohm's law states that voltage drop equals current multiplied by resistance. But let's look at what that means when you've actually got a wrench in your hand. When you crank an engine, that starter motor demands an absolute surge of current. We're talking easily 200 amps for a standard car. Now imagine just a tiny bit of invisible corrosion on a terminal, creating a measly 0.01 ohms of resistance. Well, 200 amps multiplied by 0.01 ohms, that equals a 2-volt loss. Instantly, your starter was only getting 12.6 volts to begin with, now it's trying to crank the engine on 10.6 volts. High current plus tiny resistance equals a dead car. And get this, that resistance, it turns electrical energy into heat. That tiny 0.01 ohm bad connection is literally generating 2,000 watts of heat right at the terminal.
And honestly, this is where the physics get truly wild. Most starters out there are series wound DC motors. And in these motors, the torque output is proportional to the square of the current. The square? So a 20% drop in voltage doesn't just mean a 20% drop in torque. Nope. Because of that squared relationship, a mere 20% voltage drop results in a massive 36% or even greater reduction in actual cranking power. Your starter is literally being starved of the magnetic field strength it needs to spin that flywheel.
So what actually happens inside the unit when we dip below that critical 9.0 volt failure threshold? Well, the motor can't generate enough torque to overcome engine compression, so it spins slower. Because it's spinning slower, it draws even more current, which leads to severe heating of the armature. The brushes start arcing aggressively against the commutator, which just accelerates wear. And every single time the solenoid tries to pull closed with that weak voltage, the contacts chatter and arc, causing severe pitting. You are literally cooking the starter motor from the inside out. This is exactly why throwing a new starter at a voltage drop problem just sentences that brand new part to a fiery death.
Section 3, modern tech and heavy diesels, high stakes and high compression.
Let's compare the extreme demands here. A standard gas engine needs maybe 100 to 250 amps to push past a 9-to-1, maybe 12-to-1 compression ratio. But a heavy-duty diesel? Oh man, we're talking 16-to-1 up to 23-to-1 compression ratios. Those beasts demand a massive 400 to 800 amps of current. When you're pulling double or triple the current flow, keeping your voltage drop within spec becomes incredibly difficult. That is exactly why diesels require those massive, thick 2.0 to 4.0 AWG cables compared to what you see on gas engines. Now think about how we handle dual battery systems in these big diesels. This is a classic trap I see rookies fall into all the time. Remember, electricity always takes the path of least resistance. Always. If your battery cables aren't exactly equal in length and gauge, the battery hooked up to the shorter, lower resistance path is going to take all the abuse. It ends up supplying a completely disproportionate share of that 800 amp starting current. It's going to age way faster and fail prematurely while the other battery sitting right next to it looks perfectly fine.
Equal lengths, equal gauges, no exceptions.
Okay, now let's add modern computer modules to the mix. A vehicle that's mechanically cranking slow might also trigger a whole cascade of bizarre electrical gremlins. Why? Because the engine management systems are constantly watching battery voltage. If the voltage drops too low during a crank, fuel injectors might just refuse to open properly. Transmission control modules might dump their shift memory. Body control modules will start throwing false warning lights like a Christmas tree. And those modern push-button start systems, they are incredibly picky. If they detect excessive voltage drop, they'll just lock you out entirely. They won't even attempt to crank, and they'll flash a weak battery warning on the dash, even if the battery is 100% fully charged. And all of this havoc can be caused by just one corroded ground strap.
All right, Section 4, the multimeter load test. Time to pop the hood.
Let's walk through the exact live testing procedure using your digital multimeter set to DC volts. The absolute key insight here is that we are measuring across a section of the circuit, not from positive to negative. We are measuring the loss itself. Step 1. Connect your positive meter lead directly to the battery positive post. I mean the actual lead post, not the clamp. Step 2. Take the negative meter lead and connect it all the way down to the starter motor positive terminal stud. Step 3. Disable the fuel or ignition system so the engine won't actually fire up, and crank the engine to apply that heavy load. Step 4. Read your screen. The number staring back at you? That is the exact amount of voltage getting lost to resistance in that specific run of cable.
Moving to Section 5, pinpointing the hidden faults. Let's find that invisible enemy.
So how do you definitively prove what's broken? Well, if your total voltage drop passes the test, meaning it's nice and low, but the starter still cranks terribly or fails a bench no-load current test, condemn the starter. The motor has internal damage. But if the voltage drop fails, meaning you are losing way too much voltage through the wires, listen to me. Do not touch that starter. You have a wiring resistance fault. You've got to repair those cables, clean up the terminals, or fix the solenoid contacts first, and only then do you retest the system. I really need you to burn these industry standard numbers into your memory. The absolute maximum allowable total system voltage drop is 0.7 volts. That breaks down to a maximum of 0.5 volts lost on the entire positive side, so that's from the battery post, through the cables, through the solenoid, right to the starter stud. And then a maximum of 0.2 volts lost on the negative side. Listen, any single connection, like just one battery clamp showing more than 0.1 volts of drop while you're cranking, that needs your immediate attention. And that brings me to a massive veteran insider secret of the trade. Whatever you do, do not forget the ground side. Seriously, techs routinely test the positive cable, see it's totally fine, and just assume the starter is toast. But you gotta remember, the ground return path carries the exact same 200 to 800 amps right back to the battery. A corroded engine to chassis ground strap, or maybe an engine block that someone got carried away painting, creates a massive electrical bottleneck. Ground side issues are easily the most misdiagnosed faults in the entire shop. Always, always test from the starter casing back to the negative battery post during a crank. Finally, Section 6, Maintenance and Repair Standards. Let's talk standard operating procedures. We have got to catch this corrosion before it leaves someone stranded. Every 12 months, get in there and physically inspect and clean those battery terminals. Don't just eyeball them, actually clean them. Every 24 months, perform the full cranking voltage drop test we just walked through and pay special attention to inspecting those braided ground straps. Between the 36 and 48-month mark, you should be properly load testing the battery, and if you notice any cranking symptoms at all, inspect the starter solenoid contacts for pitting. Oh, and a quick tip, when you do have to build and replace a cable, always use proper hydraulic crimps, tinned copper terminals, and for the love of God, apply some dielectric grease. Well, apprentices, we've covered the actual physics, the live multimeter techniques, and the massive destructive impact of unseen resistance. You now have the exact knowledge required to save your customers money, save yourselves hours of absolute frustration, and actually fix the real root problem. So the question I leave you with today is this. The next time a heavy truck rolls into your bay with a slow crank, are you ready to test the physics and fix the root cause, or are you just going to load another expensive part into the cannon?